As promised, here's a review for your logarithms assessment. I'll try to give you some samples. The first thing that I would like to review is how to convert between exponent form and log form. So let's say, for instance, you had the exponential function in the form of exponents, y equals 3 to the x power. The y would be your answer, or the output. The 3 would be the base, and the x would be the exponent. We're going to transform this same relationship into log form. And the important part to realize is the setup of that. So you have your log with a base as the subscript of the answer, and that's equal to the exponent, which I'll abbreviate here as exp. I'm going to take this exponent form and transform it into log form. I'm going to begin by putting the word log. And then I'm going to put the base that we're working with. In this case, it's a 3. That goes as a subscript. We put the answer, which is a y here. And that would equal the exponent, which is the x here. Here is how you would express that same relationship in log form. And we could look at a case with less variables, such as if we were looking at the exponent form 5 to the 4th power, which we could find on our calculator to be 625. That's an exponent form. I could express this same relationship in a log form using that setup by beginning by putting the abbreviation for logarithm, which is log. Now the base would be the 5. The exponent would be 4. And the power, or the answer, would be the 625. So in log form, it would be log base, the base is 5, that goes as the subscript, of the answer, which is 625, is equal to the exponent, which in this case is a 4. Here you have two different ways of expressing the same relationship, exponent form and log form. Also can be called logarithmic form. And the next piece of this would be to understand how the graphs of exponential functions behave. Right here we have an example of a real-world situation of exponential functions where you have time as your input, or the x, and your value of the bond as the y. And due to the nature of a bond, it's an exponential function. Right here we have our initial amount, and then the time is grown in a steady way, but the value is growing drastically in an exponential fashion. We could also look at a case that was exponential growth. We could look at a case of exponential decay, where we have another exponential function, but now we're looking at radioactive decay, where you start off with a certain percentage of the mass remaining in that substance, and then you have time, which is in this case growing in thousands of years, and the values are decreasing exponentially. And what you'll notice is that in both of those cases the graph never touches the x-axis, and we call that asymptotic. It gets really close to touching the x-axis, but will never actually do so. That's how an exponential function behaves. And if we were to look at the graph of a logarithmic function, the logarithmic function is the inverse of the exponential function. So if we were to look at that relationship, we would see that the two graphs reflect over the line y equals x. In this case, that black graph here is f of x, or the output y, equals 2 to the x power, which is our exponential graph. We have the line y equals x, and this other blue graph reflects over that line y equals x, making this the inverse function, since exponential functions and logarithmic functions are inverses of each other. And the inverse would be written in the form f inverse of x is equal to the log with a base of 2 of x. So that's a little bit of a word on how those graphs behave. Another feature that's important to realize is how when you're looking at the graph of an exponential function, such as y or f of x equals 2 to the x, you'll always see that that graph passes through the point 0, 1. And that's always the case with an exponential function, which would imply that the y-intercept of an exponential function will always be equal to 0, 1, since x equals 0 and y equals 1. The y-intercept is always at the point where the graph hits the y-axis, and also where the x value is equal to 0. Another important feature to realize is how we could use our product rule, quotient rule, and our power rule to simplify expressions involving logarithms. So through this packet, I'll choose a few that can demonstrate that. If you look into your Algebra 2 mixed review packet, we could take a look at number 4, where you have the log. So now this is going into logarithmic properties or rules. Such as you have the expression the log of 4m squared. We're going to be utilizing two powers here. We're going to be using the product rule, since 4 times m squared is happening, and also we're squaring m, so we're going to use also the power rule. So use the product rule first to break apart that log of a product. And then we're going to go ahead and utilize the power rule. So the log rule for a product rule is that the log of a product, such as the one given 4 times m squared, can be broken up into the sum of the logs of the factors. So I'm going to take the log of 4 in this case, and I'm going to add it to the log of m squared. The log of a product is equal to the sum of the logs of the factors of the product. That's using the product rule first. Now we see that we can simplify the log of m squared. Bring down the log of 4. And the log of a power is equal to the exponent, which is in this case the 2 jumps down as the coefficient. It's equal to the exponent times the log of the base of that power, which was m. So therefore we could express this in a simpler way as the log of 4 plus 2 times the log of m, which is an appropriate way of expressing that in simplest form. What others might do is express the 4, simplify the log of 4, by expressing it as the log of 2 squared, and using that power rule again. That 2 is going to come down in front of the log, and it's going to become 2 times the log of the base of the power, which is 2. So this would equal 2 times the log of 2 plus our second piece of this sum, which would be 2 times the log of m.